All right, welcome back. We are going to be finishing up our module on z-scores by connecting it to some of the major earlier concepts, specifically the idea of the normal distribution. This is a really important portion, not just of this section, but of the framework we're putting together, that idea of hypothesis testing. So make sure that you're really familiar with the ideas behind this and that you keep an eye for how this material is used in the next couple modules too. So, starting at the beginning, z-scores again allow us to come up with this way of standardizing scores by just representing them by how many standard deviations from the mean an individual score is. Here's where they tie into our concept of distributions. We can take an entire distribution of scores and represent them as z-scores. Now, we don't actually do this manually. We don't go in and type in every single number. That would take a long time. But what we can do is we can take a distribution of scores on any variable that we're interested in and just say, what if we turn the entire distribution into z-scores? What would it look like? Again, some basic things come to mind pretty quickly. The relation of scores to each other doesn't change when you change them into z-scores. The order of the scores is the same. Again, if you were higher than a different person on your original score, you'll also be higher on your z-score, etc. So the shape doesn't change. Whatever the shape of the original distribution of raw scores looked like, that's what the z distribution will look like, the distribution of z-scores. If your original distribution is skewed or bimodal or any of that sort of stuff, any sort of non-normal curve, the z distribution will have the same shape. However, we generally assume that scores in the population follow a normal curve, and so the z distributions we make from those scores would also follow a normal curve. We're going to get more into the nuts and bolts of why that's the case a little later on, but for now, that's just an assumption that we make, and it's a pretty safe assumption. So, a couple of things about those distributions of z-scores. Again, this standardizes entire distributions of scores so we can compare wildly different variables with totally different means and standard deviations to each other. All of those z distributions always have the same mean. That mean is 0. The reason why? No matter what your original mean was, whether it was 1 point or a million points, a score that was smack on that average is always going to have a z-score of 0. It's 0 standard deviations away from the mean. It is the mean. So no matter what your original distribution looked like in terms of those descriptive stats, the mean score of the z distribution is always 0 because that's what a score that's smack on average is always going to get for a z-score. By the same token, the standard deviation is always 1. No matter what the original standard deviation was, whether it's really, really small or really, really big, again, 1 standard deviation above average is a z-score of 1. 1 standard deviation below average is a z-score of -1. It all standardizes, so if you're 1 standard deviation away, no matter what that original standard deviation was, you get a z-score of 1 or -1. So those descriptive stats become universal now. We can represent distributions of scores on any variable by having a mean z-score of 0 and a standard deviation z-score of 1. So the advantage again is standardization. It lets us easily compare scores from totally different distributions or different scores from the same distribution of scores. We can make almost any comparison we want if we can convert the variables into z-scores and assume that they all follow a normal curve. So representing those scores as z-scores, making those hypothetical z distributions, it really, really becomes useful when we integrate it with the characteristics of the normal distribution. So to recap a little bit on the normal distribution, because we haven't seen it in a little while, but it's definitely one of our best friends in the course. We're going to learn a lot about it. Again, we assume that most variables that we study in psychology follow a normal distribution in the population. Again, it's a safe assumption. We'll talk a little more about why in future modules. Normal distribution is unimodal, one peak, it's symmetrical. Again, scores are most frequent closer to the mean. The closer to the mean you get, the more frequent scores are. The farther away from the mean you get in either direction, the more improbable or unlikely or infrequent those scores become. And again, it's symmetrical, so this left downward slope is a perfect mirror image of this rightward downward slope. The farther and farther away you get from the mean, the more improbable your scores are. How can we use this with a z-score? We can represent that normal curve in terms of a z distribution. We can say, okay, here's the middle, z-score of 0, that's right on the mean. Every standard deviation away, your z-score goes up by 1. Because of the characteristics of the normal curve, we can take any variable represented as z-scores and place that z-score on the normal curve table. And we know exactly what percentage of scores are between any 2 points in this distribution, above any score we're interested in, or below any score we're interested in. Here, we can look at basically a set of rounded numbers that shows roughly what proportion of scores in any variable that follows a normal curve are within these ranges of z-scores. 34%, about a third, a little more of a third than of a population, are between the mean and 1 standard deviation below the mean. Because it's symmetrical, another 34% are between 0 and 1 standard deviation above the mean. Between 1 and 2 standard deviations away in both directions, another 14% of people. If you add that up, that's 95% of people. Think about that. Any variable that follows a normal curve, about 95% of people are within 2 standard deviations of average. Another 2% between 2 and 3 below average and 2 and 3 above average. So about 99 out of 100 people are within 3 standard deviations of average. Scores farther than 3 standard deviations away get really uncommon. They become very, very unlikely, less than 1 in 100, eventually less than 1 in 1,000, 1 in a million, and so on. So a tool that we can use to demonstrate how this process works, how we can place these z-scores on this normal curve and make these precise calculations, involves using a normal curve table, which we'll talk about in just a moment. First, we're going to pause and talk a little bit about our first point of emphasis. This is really important. Again, z-scores, they let us standardize scores. They let us compare totally different variables to each other on a level playing field. When we combine that with the normal curve, the fact that the normal curve is typical, most variables follow that pattern, and that it has these really specific characteristics, we can compare totally different variables using that same basic framework, just using those measures of relative standing, placing different scores on a population distribution. This is a major, major step forward towards those tests of statistical significance that we're working towards. Again, that's the big goal of the first half of this course, is devising those tests and using them to test hypotheses. So, the practice problem section, the practice quiz that you'll see underneath this, it has several problems where you're going to use z-scores, you're going to place them on the normal distribution. You're going to use the normal curve table to do this. It's a downloadable document that you'll find in this modules folder. But what we're going to learn to do, take z-scores that we're interested in and find what percentile they're in. What percentage of scores are below this number or above this number. We're also going to practice taking percentiles that we're interested in and finding the z-score that corresponds with it. What's the minimum z-score you'd need to be in the top 5% of a distribution, or the bottom 10%? What's the minimum z-score you need to be in that bottom 10%? So we take percentiles we're interested in and find z-scores that match on them as well. There's several problems like this in the homework and the textbook as well. Again, for your practice problems, your practice quiz, you'll have to download that normal curve table. Here's the advantage of doing this. This is a simulation of an essential part of hypothesis testing. We take that normal curve, we designate portions of it as meaningful, as special. Basically, results that are in that meaningful area are considered statistically significant. Results that are not in that meaningful area are considered inconclusive or non-significant. So we're simulating that idea of finding points of interest in that normal distribution and finding the z-scores that match up with them. So we'll be doing something quite a bit like this in hypothesis testing, but it happens much more quickly. So don't fixate on looking up the numbers appropriately, that sort of thing. Again, emphasize that idea of taking that normal curve, chopping it up into different sections, finding points in it we're interested in, and being able to use the z-scores to say very specific things about those points. All right, this is a point of emphasis 1.5 because it kind of relates to the other one. Again, the power of this is that if you know a z-score, or just have a z-score you're interested in, and the variable follows a normal curve in the population, you can calculate very accurately, very precisely, the percentage of scores above that z-score, below that z-score, or between any two z-scores. And here's the key part, without knowing anybody else's score in the entire population. It's incredibly powerful, the amount of precision we can get, the amount of information we can get from two descriptive statistics that we turn into a z-score and an individual z-score that we're interested in. So you can again flip that. If you have a percentile you're interested in, you can find the z-score that matches with it, and you can convert it to a raw score if you need to as well. Again, this is a big part of the process of finding statistical significance. We take a percentile that we're interested in, we figure out where that percentile starts, like what z-score matches up with it. What z-score would be the boundary of that area of the normal curve. We say any result that falls beyond that point is statistically significant. Anything that falls short is not. Much more to come on that as we move forward. So to recap, again, it's that idea of using standard deviations and means to represent relative standing of individual scores, and using that to compare totally different distributions to each other. We've only learned how to do this with individual scores. Usually in research we care about sample means. That's coming up in the next couple of modules. We're going to talk about how we adjust this process when we want to look at the relative standing of sample means. And again, we can take a distribution of scores and represent them all as z-scores, and use that to represent, again, how frequent or infrequent, how probable or improbable certain z-scores are in a normal distribution. Here's some of the characteristics of it, which we've already talked about, but again, the big advantage there is we can leverage just a little bit of information into a very precise estimate of the proportion of scores in entire populations, above and below any score or between any two scores. And again, we can reverse that process, which you'll get some practice doing there as well. All right, that is the end of the Module 5 content. The next up is to practice some of those problems, to review your textbook. Again, focus on how we use z-scores to learn things about normal distributions, more than the nuts and bolts of how you're actually running these tasks. All right, you've reached the end of another module. Move on to your practice questions and your homework, and I will see you on the next module, which is all about probability.